Uh, we have been doing some problem with the quantum numbers, so I want to finish those today and start chapter 7. So here is a problem in slide number 13. I was working with the slide number 13, and the problem in question number 3. So the question number 3 is, how many nodal planes exist for a 5D orbital? So I have not taught this concept. I will talk a little bit later about the nodal plane. Basically, nodal plane is like this. So this is the S orbital. So there is no plane. This is a soccer ball, and there is a possibility of finding the electron everywhere here. So for S orbital, nodal plane is 0. There are no nodal plane. Everywhere is a possibility of finding electron. So if the orbital is p orbital, sorry, so this is not that good. So let's say this is a p orbital here. So you can find the electron here, 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 and here, 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 but you can't find the electron along this plane through the nucleus, like this plane. So for p orbital, there is a one plane where you can't find the electron. So p orbital has one nodal plane, one plane where you can find the electron. So for p orbital, nodal plane is 1. For s orbital, nodal plane is 0. For d orbital, let's say d orbital looks like this. So looks like this. So you can't find the electron along this plane here, and you can't find the electron along this plane here. So d orbital has two nodal planes. So the planes where you can't find the electron is called the nodal plane. So if you see the S, so there are 0 nodal plane, meaning that you can find electron everywhere in that orbital. For the P, so nodal plane is 1. You can find everywhere here the electron here and here, but along this plane you can't find the electron. So for P, nodal plane is 1. And then for D, so you cannot find the electron along this plane. You cannot find the electron along this plane, but you can find the electron in these lobes here. So for D, there are two nodal planes. There are SPD. Two nodal planes here. So we'll talk about that in the next slide. Now let's work on slide number 14. For slide number 14, which is the following? Which of the following is a valid set of quantum number for an electron of hydrogen atom? So there is n is equals to 1 in the first one. N is equals to 1. So if n is equals to 1, write L equals to what? L equals to, you need to start from 0. You cannot go up to 1, 0. So you cannot go up to 1. For ML, now you have to write from 0 to plus 0, minus 0 to minus 0. Like, or you can say minus 0, 0, and plus 0. So 0 meaning that same 0. So like this, yeah? And then MS can have two values. So plus half or minus half. So do we have that one in the question A? No, n equals to 1. They have n equals to 1. L equals to 0, they have L equals to 0. ML equals to 0, they have ML equals to 0, but they have MS is equals to 1. So A is wrong. Make sense? So A is wrong. Now, so A is wrong. So A is wrong. Now let's look B. So look B. So in B, what they have is N is equals to 1, L equals to 0, ML is equals to 1, and MS is equals to plus half. Now look here, N is equals to 1, N is equals to 1. We have N equals to 1, that's good. L is equals to 0, L equals to 0, that's good. ML is equals to 1, here ML is equals to 1. So when you have N is equals to 1, L equals to 0, you don't have ML is equals to 1. So this is wrong. So, but this is good. So since this one is wrong, so everything is wrong. So there is no ML equals to 1 here. Make sense? Good. Now let's look C. I think that I wrote was a C. Now let's look another one. So N is equals to 1 here, L is equals to 1 here, ML is equals to 0 here, and MS is equals to half. MS is equals to half. Plus half or minus half is a B. So minus half. So start to look here. So these are the right quantum number. Is it right or wrong? So we look here. So N equals to 1. This is good. This is like this. It's good. L equals to 0. We have L equals to 0 here, but it's L is equals to 1 here. So L is equal, it's not there. So this is wrong. So now look at number D. D. N is equals to 1. L is equals to 0. ML is equals to 0. MS is equals to minus half. Look here. We have N equals to 1. So good. L equals to 0. This is good. ML equals to 0. This is good. MS is equal to either plus half or minus half. This is good. So number D is right. Any question here? I think it's good. Yeah. So we don't have much people here. Only one student. All right. So we are done with the question number 1. Let's look the 37. So slide number 14. Question number, there was a 37. I pulled from the book. So first of all, in number A we have. So first of all, in number A, N is equals to 4. Now N equals to 4. Let's write all possible quantum number there and solve the problem we have. First, we have N equals to 4. Now write L is equals to start from 0. So 0, 1, 2, 3. Don't go up to 4. We cannot go up to 4, right? We can only go up to 3. Now, if we have 0, so ML. So ML is, so it's coming from 0 is, so let's write like this. So coming from 0 here is 0. Coming from 1 is minus 1, 0 and plus 1. And coming from 2 is minus 2, minus 1, 0, plus 1 and plus 2. And plus 2. And coming from 3 is minus 3, minus 2, minus 1, 0, plus 1, plus 2, and plus 3. So like this. So if L is equal to 0, we have ML equals to 0. If we have L equals to 1, the ML is equals to minus 1, 0, and plus 1. If L equals to 2, we have minus 2, minus 1, 0, plus 1, plus 2. This ML value. If L is equals to 3 here, minus 3 to plus 3. So they are the magnetic quantum number. We write that way. Yeah. Good. Now, what is the question here? N is equals to 4. We have N is equals to 4. And then in number A, L is equals to 2. ML is equals to 0. And MS is equals to 0. So first of all, we write here, MS cannot be 0, 1, 2, 3. MS is always plus half or minus half, right? So this is clearly wrong. This is wrong. So everything is wrong. So A is wrong. Now let's look B. B is equals B. In number B, we have N is equals to 3. So if we have N is equals to 3, so I write N equals to 3 here. So I write the N equals to 0, 1, 2. I cannot go up to 3. So like this. So if N equals to 3, 0, 1, and 2. So ML have this one. Yeah. So now let's look number B. So we have in number B, N is equals to 3. L is equals to 1. Then ML is equals to minus 3, and MS is equals to minus half. So this is good. MS is minus half is good. Now let's look ML equals to minus 3. Do we have minus 3 here? We don't have. When N is equals to 3, we don't have minus 3 here, right? There is nowhere is minus 3. So we We don't have this one, so this is wrong. So everything is wrong here. Make sense? So first write the all possible quantum number and compare if that is there or not. Yeah, good. Now let's look question number C. So n is equals to 3. For n equals to 3, all quantum number are this. In number C, n is equals to 3. This is number C. N equals to 3. Down n equals to 3, and I think L is equals to 3. L is equals to 3, and ML is equals to -1, and then MS is equals to plus half. MS is equals to plus half. So MS is equals to plus half. This is good. MS can be minus half or plus half, right? This is good. Now ML is equals to -1. So ML is equal to -1 is somewhere there, right here. -2, -1, 0, right? This is good. This is good. L is equals to 3. Do I have L is equals to 3 here? No, right? L is equals, we have 0, 1, and 2. So I don't have this number in this set of quantum number along this line, L equal to 0, 1, 2. So this is wrong. So everything is wrong. Yeah? So number C is wrong. Make sense? Good. So now let's go to the next slide. Number 38. So I'm in the slide number 15. So slide number 15, question number 38. So let's look n equals to 2. So first of all, n is equals to 2 here. So let's write all possible quantum number here. N is when n equals to 2, n is equals to 0, 1. It cannot go up to 2, right? 0 and 1. Now, if we have a L equals to 0, ML will be, for this 0, we have only 0, -0, plus 0, or 0, right? So that means only 0. Now for this one, we have -1, 0, and +1. So we have these three quantum numbers here, like this. Yeah. So let's look question number 8. So in A, we have A is equals to 2. L is equals to, sorry, n is equals to 2. I mean A. N is equals to 2. L is equals to 2. ML is equals to 0. MS is equals to plus half. So this is good. MS is equal to plus half is good. Either plus half or minus half. That's good, right? This one is good. Now look at ML equals to 0. So if you look at ML equals to 0, you can find 0 here, sorry, 0 here, 0 here. Probably that's good, right? So I can find that one. Now this is good. Now let's look at L equals to 2. Do I have L equals to 2 here? I have only up to 1, right? 0 and 1. There is no 2, right? L equals to 2. L is equals to 0 and 1, but it says L equals to 2. So there is no L is equals to 2. So this is wrong. So everything is wrong. Any question here? All right, so let's look B. In number B, again, in number B, n is equals to 2. So number B, again, n is equals to 2, L is equals to 1, L is equals to 1, ML is equals to -1, and MS is equals to 0. MS is equals to 0. So I told you MS, this spin quantum number cannot be 0. It can either be -1 and +1. So this is 0. So this is wrong. So everything is wrong. So when MS is equals to not -1 or not minus half or not minus half or plus half, all the thing is wrong. MS must be either -1 by 2, or +1 by 2. If there is no -1 by 2 and +1 by 2, everything is wrong. So we don't have to look other things. So that's a B, right? Now let's look C. So the easiest would be if there is a MS is not equal to +half and -half, that would be the most easiest to find out whether it is wrong or right? Now let's look at n is equals to C. Number C, n is equals to 3, L is equals to 1, ML is equals to ml is equals to minus 2 and ms is equals to plus half. Plus half. So ms is equal to plus half here. So this is good. This is good. This is good. Now, now let's look ml equals to minus 2. Sorry, I have not written n is equals to 3 here. Let's write everything. N is equals to 3 here. So L equal to 0, 1, and 2. 0, 1, and 2. For N is equals to 3, right? 0, 1, and 2. And for M, for this 0, this comes there. For this 1, this 3. For plus 2, we have minus 2, minus 1, 0, plus 1, and plus 2. These are ML quantum number for 2, right? L equals to 2. Now, here L is equals to 1. You see, this is the box they are talking about. L is equals to not 0, not 2. They are talking about L equals to 1, right? Yeah, L equals to 1. See? This is the L equals to 1. So he's talking about L equals to 1. So along this line, do we have, for L equals to 1, do I have a here? No, right? So there is no plus 2 or minus 2 or anything like that along this line here. So this is clearly wrong. From L is equals to 1, ML cannot be 2. So this is a P. So L is P orbital like this. So L means SP, 1 is P. P is like this. Like this. And the ML is 2. It is saying that this is a double dumbbell or something like this. So from this comes to this. It's not possible. Make sense? So ML2 means something like this. L is equal to 1 is P, which is something like this. This cannot come from this, right? So if the father is like this, children cannot be like this. Children should be something like this. Something like this. Good. So from this one, so although you may be confused. Last year I was teaching this and I myself confused. So, oh, so minus 2 is here. So it should be right? Minus 2. But this minus 2 is coming from this L equals to 2 line. But the question is saying this ML minus 2 is coming from the L is equals to 1 line. So L is equals to, yeah, it's not possible. Make sense? So that's wrong. So this is wrong. So everything is wrong. You know now, right? How to look the quantum number. Now, do we have anything else? Yeah, so just read those yourself. I think so. Let's look 139 and we will be good. So this kind of problem will be in exam. So which set of quantum number is wrong, right? So which is wrong there? So how to find which one is wrong and which one is not wrong. Now, state which of the following orbital cannot exist according to the quantum theory. Let's look at the which cannot be possible. Let's look at 2s. Is it possible or not? So 2s. So what is the n value here? N is, this first number is 2, right? And s means, s means S, P, D, F. So s is 1, sorry, s is 0, P is 1, D is 2, F is 3, like this. So, so S is spherical like this one, P is dumbbell like this one, D is double dumbbell like this one. Double dumbbell like this one, yeah? And then F, I don't know how does that look like. All right, so S is, so S means that L, that is L. L equals to, it is said 0. S means 0. So N is 2, S is 0 here, yeah? Make sense? L is equals to 0. So L equals to 0, 0 orbital is we give as a S in the name S. Can it exist or not? So let's look. So if we have N is equals to 2, what are the possible quantum number here? 0 and 1, right? Yeah, 0 and 1. So N is equals to 2. We start from 0 and we don't reach up to 2. So we don't only go up to 1. So do we have N equals to 2 here? Yes, we have 2 here. Do we have N equals to 0 here? Yes. So this is exists. This is possible, right? It's exactly according to the root, right? Now let's look another one, 2D. So here is a 2D. Is it possible or not? Let's look at 2D. So N is 2. So S, P, D. So S is 0, P is 1, D is 2. So D is 2. So here L is equals to 2. So D means 2. So these are the azimuthal quantum number S, P, D. D means L equals to 2. Now let's write the quantum number now, right? So if it is right or not right. So when we have n equals to 2, L equals to 0 and 1. So do we have L equals to 2 here? No, right? For n equals to 2, I cannot write up to 2. For azimuthal quantum number, I can only go up to 0 and 1, but not up to this number, right? Do I have 2 here? I have 2 here in my problem, but the theory says you cannot go up to 2. So this is wrong. This cannot exist. Make sense? Good. So how about 3p? So let's look 3p. Is it possible or not possible? 3p. So what is n? N is equals to 3. What is p? So p would be like this. P is so 0, 1, 2, 3. So this is S, this is P, this is D, this is F in L. So L is equals to, I should write 0, 1, and 2 because L is equals to 3. I started from 0 and I can't go up to 3. 0, 1, and 2. Now 3p. So that looks like that one. So this is n equals to 3. S this p means not 0, not 2, but 1. So like this. So n equals to 3 means L equals to 1, right? So n equals to 3, L equals to 1. P means 1. Yeah? So S means 0, P means 1, T means 2, right? And F means 3. So is it possible, does it exist or not exist? Let's write the quantum number. N equals to 3. L equals to 0, 1, 2. Yeah? And I don't have to go to ML. It doesn't write ML right now. So do I have 3? Yes, I have 3. Do I have 1? Yes, I have 1. So this exists. 3p exists. Yeah? Good. Now let's practice one more. 5s. Now let's like the 5s. So there is a 5s. So maybe I write the 3f. Let's write the 3f. So 3f. Is it possible or not possible? So n is equals to, here n is equals to 3. N equals to 3. So S is 0, P is 1, D is 2, F is 3. So F is 3. So L is 3 here. Make sense? So S is 0, P is 1, D is 2, F is 3. Yeah? That's the azimuthal quantum number. Is it possible or not possible? Let's write all quantum number here. So for n is equals to 3, I'm trying for n equals to 3. Now L would be 0, 1, 2. 0, 1, 2. Can I go up to 3? I can't go up to 3, right? So here is a 3, but according to rule, I can't go up to 3. So 3f clearly cannot exist. Yeah? 3f. I don't see 3f because n equals to 3. This 3 is here, n equals to 3. When L equals to 0, 1, 2. I can't write up to 3. So 3f is not possible. Make sense? Now let's write 4f. Is 4f possible or not? So 4f. SPDF. SPD. Yes, right. 0, 1, 2. So n is equals to 4, right? Now F means what? S is 0, P is 1, D is 2, F is 3, right? F is 3. So F is 3. So 4 and 3. So this 4F means n is 4, L is 3. Now do those quantum number exist or not? Let's write the quantum number according to rule. N is equals to 4. Now L should be 0, 1, 2, and 3. I cannot go up to 4 here, right? I can only go up to 3. Do I have 3 here? Yes, I have. Do I have 3 here? Yes, I have 3. So this exists. Make sense? Alrighty. So now let's look one more. 5s. So this is good. Now 5s. So this is 5s. So n is equals to 5. S is equals to, so sorry, that's a L. L is equals to, S means 0. S is 0, P is 1, D is 2, F is 3, right? So S is 0. I have this quantum number. Does it exist? Let's write the quantum number. So n is equals to 5. So this is the given in the problem. This is the rule. N equals to 5. L equals to 0, 1, 2, 3, 4. I cannot write up to 5, right? I can only go up to 4 for L. Now, do I have n equals to 5 here? Yes, I have n equals to 5. Do I have n equals to 0? Yes. Both way we have the number, right? So that means that exists. Good. So now let's look at 28. So this is a question number 28. And when n equals to 4, l equals to 2, and nml equals to -1, to what orbital type does this refer? So it is giving like this. So let's look at this one. So question number 28. So n is equals to 4. He's saying n equals to 4, and l is equals to 2, and ml is equals to -1. So which kind of the orbital it is? So n is equals to 4. I write 4 here, and what is the name of this one? So S is 0, P is 1, D is 2, right? So this 2 is D. 2 means D. So S is 0, P is 1, D is 2. So I have 2 here, so that is D. 4D. 4D. And how about this one? So it could be a dxy, could be dyz, could be dx square y square. There are 5 double dumbbells. So this is double dumbbell type. So this orbital is double dumbbell type. So how many type of double dumbbell there? There are 5 double dumbbells. So that could be anything. So I just write 4D. It can be 4dx y, 4dxz, 4dx square y square, 4dz square, whatever. Yeah. Good. So this one is a 4, and then D2 means D. Sorry, L equals to 2 means D. I don't go here because it can be like this. It can be like this. So there are 5 kinds. So I don't know which kind is this one. So for D is enough. Now let's look another one. How many orbitals occur in n equals to 5? So it's very simple. So how many orbitals occurs n equals to 5? We have a rule n square. So n square equals to 5 square, that's 25. So that many orbital exists there. Yeah? 25. So if you start to write n equals to 5, there will be 25. So like this, n equals to 5, then you will write, sorry, here n square. So number of orbital would be 5 square would be 25. So n equals to 5, n equals to 0, 1, 2, 3, 4, like this, right? And then you need to write the ml is equals to, from this 0 comes 0, from this 1 comes -1, 0, -1, 0, +1, from this 2, -2, -1, 0, +1, +2, from this 3, -3, -2, -1, 0, +1, +2, right? +3, up to +3, right? From -3 to +3, right? And then for 4, n equals to 4, -4, -3, -2, -1, 0, +1, +2, +3, +4, right? Like this, right? So if you count this, there are 25. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So maybe I just counted mistake in 26, but there are 25. Yeah? Good. Like that. So you just write those and you count these ml numbers and you will see 25 here. Yeah? All ml. Good. Now, do I have a what's that one? How many orbital occur in F subcell? So 29. Possibly excited state, whatever. So just it's okay. Just ignore those. Yeah. Just know how to write the quantum number. Which set of quantum number is right? Which set of quantum number is wrong? So they are important. Yeah. So they are trying to say the same thing in different language. Yeah. So as long as you know how to write the quantum number, you are good. So if n is equals to 4, I might say, what are the quantum number? All quantum number for n equals to 4. N is equals to 0, 1, 2, 3, not up to 4, right? And what are the ml values for this one? So I just got like this here. So for this one, n equals to 0. For this l is equals to 1, I have -1, 0, +1. For l equals to 2, I have -2, -1, 0, +1, +2. and for these 3 minus ml values are minus 3, minus 2, minus 1, 0, plus 1, plus 2, and plus 3, minus 3 to plus 3. Yeah? So that's like that. So just write, learn to write like that. Yeah? So that's important. Alrighty. So we are done with this slide. Now let's go to the slide number 18. So slide number 18. So this is very complicated. We just take one simple example here. Let's talk about the 1s orbital. So let's go to the slide number 18. So other things are just they are repeating the same thing. Yeah. So slide number 18. So slide number 18. So s orbital looks like this. S orbital looks like this, like a soccer ball or golf ball, you can say. So it's not a plane. It's like the ball, right? So there is one electron. There is one electron in one orbital. Let's say in a hydrogen atom, there is one. This is a 1s orbital, and this is the first orbit, and then this is spherical, and there is one electron here. So there is one electron here. So this is the nucleus. Where does that nucleus spend most of the? This is the nucleus, and there is one electron. This is one electron here. So where does this electron spend most of this time in its entire life? Yeah. So it's just like, where do I spend most of my time in United States? Is it in Texas, or is it in Wisconsin, or is it in Boston, Massachusetts? Where do I spend most of my time, right? So this is the Earth, like the Earth, and this is me. So in my entire life, where will I spend my time the most, right? So that's the problem 18 is showing, yeah? So this is the electron. So this electron is jumping everywhere. So it's just like I'm traveling. Sometime I went to Germany, sometime I went to United States, sometime I went to Texas, sometime I spend my time in Boston, and sometime in Rhode Island, and now I'm in Wisconsin, right? So I just count in which state I spend most of the time, right? Is it in Massachusetts? Is it in Germany? Is it in Wisconsin? Or is it in Texas, right? Or where did I spend? And I was born in Nepal, and which place I spend most of the time as an electron. Suppose I am the electron, and this is the spherical space like the Earth. Where do I spend most of my time, right? So the scientists, the people who doing the calculation, calculated this thing and found that, oh, this electron can jump everywhere inside this place except the nucleus, but there is a particular space where this electron spend most of his time, right? So just like this, there is a board here. Let's say this is a board here, and this board is, I don't know if I write this is a board here, and like the electron, and this is Earth, and it is just flying everywhere in the Earth except at the center of the Earth, right? But it looks like that at a certain radius, somewhere here in this place, this body spent the most of its life. Maybe there is the grapes, right? Maybe there is a good food here along this line, along this radius. So most of the time, this body spends its time along this region. But it also goes everywhere around these places. But most of its time is spent here. Make sense? So that's what the question. Slide number 8 is showing. Yeah. So the orbital is spherical here. The electron cannot be here. Electron can never be in the nucleus. So never possible to come to nucleus. But it is spend its time everywhere in other places. But most of the time. So if there is 100 years of electron's life, maybe 80 years it is spent along this region. Along this region, another 20 years it will spend in other places, either inside here or outside here. 20, but other 80 years he will spend here. Make sense? So that's what it is saying. The calculation shows something like this. So if you plot this data in probability diagram, it looks like this. So like this, yeah. So if you see here, this is a nucleus. Electron never comes in the nucleus. So 0 probability. This is the probability of finding electron. Probability of finding electron in nucleus is 0. So this is 0 point, right? So electron never comes here. So electron can be found here a little bit. Electron can be found here a little bit higher. Electron can be found here a little bit higher. The maximum time the electron is found right there from 0 to this distance. Make sense? And then what happens after that? If I go here, electron cannot be found that much. The probability decrease. And if I go outside of this region somewhere here, that far distance, the electron cannot be found right here. That is, yeah. So there is a sucker ball. So within that sucker ball, we can find the electron. And within that sucker ball, there is a specific region where the electron can be found the maximum time. Yeah. Electron cannot be found in the nucleus, and electron cannot be found outside of the sucker ball here. Yeah. Like so that tells that. Make sense? Good. Alrighty. So it looks like electron spent most of its time in one picometer. So is it a picometer? So yeah, 52.9 picometers. So from here to this distance is a 52.9 picometer, very small distance. So where can we find the electron in maximum time in hydrogen atom? From nucleus to this place, 52.9 picometer. Yeah. Where is the electron in hydrogen atom? Where does the electron spend most of the time of its entire life? Is from nucleus. From 52.9 picometer, electron can be spending its whole most of its time. Yeah. And then again, where cannot find the electron? We cannot find in nucleus. And where, in which place we cannot find the electron again? In the 5 multiplied by 52.59 picometer. Where this is about 5 multiplied by 52 is about 250, about 230, right? So you can find electron maximum at 52.9 picometer, and again you multiply this number by 5 and it comes to be, this is about 53, and multiply by 5 would be let's say about 300, yeah, 53 multiplied by 5, so that would be about 53 multiplied by 5, 15, so about 265 picometer. From this is from here to here is 265 picometers. So here you cannot find the electron outside of that. Make sense? So that's what it is saying. Alrighty. So here you can find the electron. That means here you can find the electron. You can find the maximum time the electron spend its time in, from 0 to 52.9 picometer here. And the electron spend some time around this region also, but electron never spend its time in the nucleus. It never falls into the nucleus. That's what it is. Make sense? So there are a lot of other orbitals. I'm just talking about the 1s orbital of the hydrogen atom, but there are a lot of other orbitals we don't study in this course. Yeah. Good. So that means that. Alrighty, everyone. So let's look this one. Now I have one thing to talk about the nodal plane. So I already told you. So what is the nodal plane? So nodal plane is a place where electron cannot be found. So let's say this is a spherical orbital here. This is a spherical orbital here. So you only cannot find the electron in nucleus. You can find electron everywhere within the surface, right? So how many planes there you can't find the electron? 0. So for s orbital, there is no planes where we can't find the electron. Everywhere we can find the electron. Make sense? So how about the nodal plane for s orbital? For s orbital is 0. You can see there. So L equals to 0. The number of nodal plane is 0. Now let's look at P. P is like this. Sorry, this is too big. This is too small. So this is the p orbital. You see, now for p orbital, you can find electron everywhere. There is also the probability where you can find the maximum and the minimum kind of thing, right? But you can find electron everywhere here. You can find electron everywhere here. Where you can, in which plane you cannot find the electron? Along this line here, you put the paper here, and along the paper you cannot find the electron. So for p orbital, number of nodal plane is 1. Make sense? So Can you put the paper here? Yeah, you can put the paper here, but you can find the electron along this plane here. You can find the electron along this plane. You can find the electron along this plane. So there is only one space plane here. There you cannot find the electron, right? So it's just like you take the two pen. So like this. So one pen is coming down like from this plane, and another pen is going up from this plane, right? So along this pen up there is a possibility of finding electron. Along the pen hanging down, you can find electron everywhere. But where you cannot find the electron is along this paper. So there's a one plane. Make sense? Good. How about the d orbital? So for p orbital, we have only one nodal plane. For p orbital, we have only one nodal plane. One nodal plane. PLANE plane. All right. Now let's look at the d orbital. F orbital we don't talk, so we only go up to d orbital. So for d orbital looks like this. So this is one lobe, this is another lobe. So they look equal. So like this. Yeah. So this is a d orbital. So you can find everywhere this electron can be found everywhere here. Where do we cannot find the electron? We cannot find the electron along this line, and we cannot find electron along this line, along this plane. So there are two planes where you cannot find the electron in d orbital. Yeah. So there are two nodal planes here for d orbital. For d orbital, two nodal plane. Along this plane, you can find electron. Along this plane, you can find the electron. So it's like this. So this is my paper here, just how I showed it previously. So this is coming this way, this is going other way, this is going other way from the board, this is coming this way. So I put this paper like this. So along this paper, there is no possibility of finding the electron. Yeah, and I place this paper like this here, and along this paper plane, there is no possibility of finding electron. Yeah, above that and below that you can find. Yeah, only along this plane you cannot find the electron. Make sense? So alrighty. So I think we are done with this chapter. Now I have 8-minute time, and so how many nodal plane here? There are two nodal plane for d orbital. Yeah? So f orbital I don't talk because I don't know how does the f orbital look like. So it doesn't make sense I talk about the nodal plane of f orbital. Good. So now let's start this chapter 7. So this is the hardest chapter. Chapter 5 is the hardest chapter. Yeah, hardest chapter. So it's a very counterintuitive. It's very hard to think what's going on there. So yesterday I posted the chapter 7 slide. So this is chapter 7. So we just enter to chapter 7. Chapter 7. Now, I already told you each electron have 4 quantum numbers, right? So we consider one electron here. Let's say this is a orbital, 1s orbital. This is a 1s orbital, right? So 1s, 2s, 2p. We will talk more about those. This is one of those orbitals. How many electrons can be here? There can be 2 electrons, only 2 electrons, and no more. So in one orbital there can be only 2 electrons. So this is one electron, this is another electron. We write like this way. So the upper going arrow like this shows that this guy is spinning to the clockwise direction, right? Because electron is a particle, and this particle is spinning like this. So rather than writing the circle here, they just write this line. This is the electron here. Yeah. So this is spinning to the clockwise direction, and there is another electron. This is spinning the other way. So there is another electron, this guy, and this is spinning this way, and they write this like this one. So this basically the pointing above arrow shows the electron is moving to the clockwise. Pointing down arrow shows there is another electron moving, rotating to the or spinning to the anti-clockwise. Yeah. Good. So how many quantum numbers this guy has? Let's write. So how many possible quantum number for this one? Let's say these are in the 1s orbital. 1s orbital. So let's say this is a 1s orbital, and there are 2 electrons. How can I write the quantum number? So n is equals to 1. So I have 2 electrons. So I'm going to write, I have 2 electrons. So I'm going to write the quantum number for this guy this way and this guy this way. Yeah. So let's say n is equals to, this is a 1s orbital. So this is 1s orbital. There are 2 electrons in the 1s orbital. So n is equals to 1, right? N is equals to 1. And then what is the S means? So L equals to 0, right? S is L equals to 0 is S. L equals to 1 is P. L equals to 2 is D. Now, now I have a N equals to 1, L equals to 1. Now I write the ML, magnetic quantum number. From 0 comes minus 0 plus 0, 0. So that's 1 is 0. Yeah? Make sense? Good. And then now I want to write the MS. In which side this electron is rotating? This is clockwise. So this guy is rotating to the clockwise spin. So that is plus half. So I wrote all possible quantum number for this my first electron. Make sense? Now I'm going to write the all possible quantum number for the second electron. So for the second electron. So this is for the first electron. Yeah, all 4 possible quantum number for first electron. Now I'm going to write the quantum number for the second electron here. So again, this is in 1s orbital. So n is equals to 1. So 1. Yeah, and then L is equals to it's in the s orbital. So this is 0. I cannot write 1. 0. I cannot go up to 1, right? 1 is 0. Now, now ML is if it's 0 minus 0 plus 0 and 0 here, so that's 1 is 0, right? Now MS. Now I wrote the plus half already here. That was moving to the clockwise, right? Now this electron is going to the counterclockwise, so I must write minus half here. Listen. So you see here, so there are 2 electrons in exactly the same seat, but one is spinning toward the clockwise, another is spinning to the anti-clockwise. So there are no 2 electrons that have exactly same 4 quantum number. So there 3 quantum numbers for 2 electrons can be same. So if you look here, these 3 numbers and these 3 numbers are same, right? The 4th quantum number here must be different for 2 electrons. If the 4 quantum number are same for 2 electrons, this 2 electron is the same guy. They are not different. There is no identity difference between the 2. Yeah. So what is the difference between these 2 electrons? There is only one difference between these 2 electrons. This guy is moving to the clockwise direction. This is moving to the anti-clockwise direction. That's the only difference in the address. Yeah. If I write the plus half here and plus half here, or minus half here and minus half, plus half, or minus half and minus half, I'm just talking the same electron. I'm not talking about the 2 electrons. So 2 electrons in an atom can never have 4 quantum number the same. At least 1 quantum number is different. So all these 3 here same, all these 3 are same, but they must be different here and here. Yeah. But if this one and this one same, maybe there is somewhere difference. Maybe there is 1, there is 0. Yeah. Make sense? Good. If there are 2 electrons in an atom or more electrons, but 2 electrons can never have the same 4 quantum number. There must be 1 quantum number difference to separate the which electron we are talking about, right? If we are talking about the plus 1, we are talking about the electron that is spinning the clockwise direction. If we are talking about the another electron that has a quantum number minus half, we are talking about the electron that is spinning to the other side. Good. So that's the first slide. Now let's look at the second slide. How much time I have? Oh, we are done. So from second slide, we will talk in the next class. So the Pauli's exclusion principle and whatever. All right. Thank you, everyone. So good luck for the exam. So 80 minutes is the time. Don't rush. So it will be plenty of time there. Yeah. Good. I'm going to stop here.